Hi, I'm Gene Fry. I began studying global warming 3 months after getting my PhD from Cornell University in 1989. I worked for the Energy Office in Maine, then for many years at the Massachusetts Utility Commission. There in 1991, I estimated dollars per ton damage values for CO2, other greenhouse gases, and other pollutants. But mostly I worked on electric energy efficiency programs, especially estimating their savings. Later, I did much the same thing for utility companies here and in Connecticut until I retired. I presented to some 60 audiences, recently as a keynote speaker on 3 continents. Since 2013, I've lobbied some 30 US senators and congressmen for a revenue-neutral US carbon tax, plus 7 times just for Massachusetts. I recently began to publish my research. So let me share my screen with you. So albedo changes drive a lot of warming. We'll look out to 2400. We can learn lessons from the distant past. The red area is much warmer than today and mostly ice-free, at least large ice sheets, gets up to 13 degrees Celsius warmer than the deep ocean now, 12 degrees warmer. Temperatures can rise suddenly as they are now. They did that 55 million years ago and 41. With more ice, temperature swings are wider since albedo changes, reflection between icy and less icy states, are larger. A quick look at the thermometer record. Sea surface in blue, land surface in red, combined in green, has increased 1.2 degrees Celsius in the last century. The rate of change has speeded up. More than 2 degrees Celsius per century. We'll pass 2 degrees at that rate in 2060 for sea plus land and 2045 for land alone. Looking at the Keeling curve, most of you have seen, not the sawtooth version, but using annual averages for CO2 by year. CO2 is up 47% since 1750, most of that since 1880. Methane is up even more, the majority of that in the 19th century. 300 parts per million is the maximum between ice ages. We know from ice cores in Vostok and elsewhere. This is current level is the highest level of CO2 in the atmosphere since 14 million years ago, when it's 430 to 465 over 400,000 years. Deep ocean's 5.6 degrees more or less warmer over those 400,000 years. Seas were 25 to 40 meters higher. 4 million years ago, it was almost as much CO2, about 4 degrees Celsius warmer, give or take, and seas were 20 to 35 meters higher. That means ice then was gone from almost all of Greenland, most of West Antarctica, and some in the east. As you may know, lots of ice is grounded below sea level in the west, but so is 1/3 in the east. Sediments show that East Antarctic ice retreated then hundreds of kilometers inland. Look at the ice core, suggests a 4.5 degrees Celsius warmer world at 400 parts per million, similar to 4 million years ago. That makes Kansas summers hotter than Las Vegas ones now. Look at the ice core data from Vostok, this one covering 425,000 years. The temperature in red, methane in green, and CO2 in blue. Both of those are currently off scale, but that's a reasonable approximation at the upper right. 2019 temperature is the highest in quite a while, but not as high as in several interglacials when the CO2 level was much lower than now. In the next slide, we'll get rid of the time axis on the bottom and plot the bottom temperature against CO2. So here we go. We'll also use the 4 and 14 million years ago data. The blue dots are CO2 temperature readings from the Vostok ice cores every 10,000 years based on the graphs you saw. The purple line is the best fit linear regression using logarithmic form for CO2, adding data for methane, gives you the green line plotted in CO2 space. Explains most of the variation. When you add methane, it explains still more. It does not explain the variation due to Milankovitch cycles, which is yet another dimension we're not exploring here. To convert the polar Vostok temperatures to global, I've used Snyder's development over 2 million years. The Vostok-derived relationships are surprisingly consistent with those from 4 and 14 million years ago. So you can see the methane levels today are even more high than the CO2 levels are higher than the Vostok. Using the green equation with both methane and CO2, we're looking at 8.5 degrees Celsius warming, but only 5.1 if methane is neglected. Of course, that's outside the range of Vostok, so take that with a grain of salt. 40% of warming in decades, the rest over centuries. So again, the equation using CO2 and methane, and a rough approximation of what we have from Carolyn Snyder for the global to Vostok conversion. We need about 317 parts per million of CO2 and 694 of methane. That means we need to remove most of the CO2 we've emitted, all future emissions, and all of our CH4, leaving a carbon budget for burning fossil fuels of negative 310 gigatons or billion tons of carbon. That's a bit over 1 trillion tons of CO2 or 1 trillion petagrams. I'm sorry, petagrams, not trillions of petagrams. Albedo, 5 major factors affect the temperature more than greenhouse gases directly: clouds, sulfate, sea ice, snow, and land ice. Water vapor, a greenhouse gas, is also very important. First one is clouds. Best study I've seen is from Zelenka 3 years ago. The cloud feedbacks, we have less cloud area in blue, more high, low, less low altitude clouds in red, but thicker and more opaque clouds in purple. The total amount is 0.47 watts per square meter per degree Celsius, which is about 3/4 of the IPCC most recent estimate, but it is Zelenka's is the one I use here. Next, sulfates. Why didn't global temperatures rise as smoothly as CO2 emissions, especially 1940 to 1975? Sulfates. The red data is 5-year averages from NASA. The green diamonds are from the regression analysis using methane, CO2, and sulfates. You see when volcanoes put sulfates in the air, major eruptions that hit the stratosphere cool Earth off quite noticeably for a few years, many months anyway. So human sulfur emissions went way up from 1940 to 1970, cooled things off for 35 years, so that they balance the CO2 increase. You take away the sulfates in the atmosphere, we put in scrubbers, and temperatures go right up. But our sulfur emissions are down only 23% from the peak. We have more than 3/4 of our sulfur emissions still to get rid of. So our sulfate levels are still 3 times 1880 levels. There's the equation of the green diamonds. The equation for sulfate is minus 0.00393 parts per billion. It's highly significant, R squared 98%, T ratio is high. And we notice that from trough to top is 1.8 degrees Celsius on land, which is warm more than the sea surface. Third factor is sea ice. Arctic ice is shrinking fast. Data from the University of Bremen, those are minimum annual Arctic sea ice area. The volume is declining faster, no surprise. POMAS model out of the University of Washington, blogged by Whitneyus. The ice gets thinner too, 3 dimensions. As a result of the decrease in the ice area, Dark water absorbs more heat, and Earth warms up more, even without more CO2. Notice that the minimum ice area fell 49% in 37 years. Volume fell even more, most of it in the last 10. Arctic Ocean could vanish by fall for a couple of days this decade and be gone all summer in 25, gone all year later this century. Speaking of later this century, our April in blue is the maximum ice area month. September in magenta is the minimum. We're looking at the minimum ice area based on 1980 to the end of that record being soon next decade. But when you look at the larger dots, that suggests it will be this decade when we have an ice-free day. And looking at the blue dots, that suggests that maybe 2 decades before the end of the century, we'll have ice-free all year round. So how much does this warm Earth's surface when you lose sea ice? Hudson estimated that total sea ice loss would be 0.7 watts per square meter, of which 0.1 had already occurred. Antarctic sea ice covers a similar area, but it's not clear that its loss has begun yet. Hit record highs, followed by record lows. This year is below, but not record low. So snow is arriving earlier, but leaving earlier. And that has an effect on the radiative cooling from the northern snow cover, 0.33 watts per square meter, about 12% added to greenhouse gas warming over the study period of 32 years. It's not just the timing, it's the total number of days which snow is on the ground, and that decreases as you go from near the equator to the poles. So using adjusted data, there are 3 adjustments, 2 for latitude with a sun angle and 1 for precipitation for 14 US and Canadian cities, shows the extent of northern snow cover, which is mostly north of the southernmost city in the analysis, which is why we did 2 latitude adjustments, decreases 9% per degree Celsius of global surface warming. The unadjusted amount is about twice that. Next, land ice. Greenland's net ice melt rate rose 7 times over the past 17 years. Antarctica tripled over 10 years. Both of those work out to about 12% a year acceleration in ice loss. But the second derivative means eventually it won't be accelerating as fast, and eventually, more eventually, it may not be losing ice more quickly, although that's centuries in the future. So there's not really a lot of effect from the land ice because it's so thick. It takes a long time to get down to 0 volume, unlike sea ice. Water vapor is a key greenhouse gas, 7% more water vapor with 1 degree warmer air. Radiative forcing 1.5, that's a lot, 4 to 5 times as much as the other things we're looking at, and almost as much as CO2 emitted since 1750. So we're going to put these feedbacks together in the past 45 years first, and then look farther out in the future all the way to 2400 using a model decadal resolution. So the observed global surface temperature warming from albedo changes over those 42 years, sulfate loss is the biggest one. And Arctic sea ice loss is smaller. There's 0.11 plus the cloud and water vapor feedback, and then you multiply it by the conversion factor. Snow cover timing change, similar. Together they amount to 0.33 degrees Celsius, which is almost 40% of the 0.839 degrees Celsius total surface warming over the 41 years. And that comes from albedo or reflectivity changes, both direct and indirect from clouds and water vapor. So Earth will warm 3 to 4 times more even if CO2 levels do not change, leading with coal sulfur emissions almost 0.4, polar sea ice a little over 0.3 each, north and south, Northern snow cover, I've calculated 0.7. Receding land ice, 0.3, but an awful lot of it's still left. Warming the oceans enough so energy out equals in, 0.2 so from the greenhouse gas level so far, and probably be more as we add greenhouse gases, plus the water vapor and cloud cover multiplier. If we keep adding greenhouse gas, don't peak till 2035, you're looking at about 5 degrees Celsius further warming, in addition to this 4, in addition to the 1.1 that we've already experienced. Quick look at permafrost, the biggest natural reservoir of carbon that may be entering the atmosphere. Twice as much carbon as the atmosphere, maybe a bit more, depending on what depth you measure it to. McDougall looked at 2 different paths of emissions and 3 different climate sensitivities. One we find is over at the right. The emissions are similar to those at the top, but because of the albedo effects, the temperature effects are like those at the bottom. And we're looking at several tenths of a degree of warming from permafrost. So how fast is this warming? Sulfur and sea ice loss, as I said before, will be complete before 2100, sulfates by 2050. Snow cover and cloud cover losses continue. Permafrost mostly over the next 3 centuries. Polar land ice loss and warming the deep ocean much longer. So here are 6 scenarios. Peak not till 2035, consistent with China's plans and also with oil company estimates. Current peak, or 2015, a couple of years ago, which is similar to 2020. Getting rid of fossil fuel used by 2050 is an orange line underneath, first the green and then the magenta. Cold turkey is stopping fossil fuel use immediately. Adding carbon dioxide removal, about 1/3 as much as we've lost from the soil, or as we've emitted from fossil fuel emissions in 2010, is the blue case, and the green case is twice as much. There's room to put some carbon back in the soil, but there are also limits to that. That leads to these concentrations of CO2, and they're instigated by our own emissions, but really filled out by emissions from the other carbon reservoirs. Permafrost, unfrozen soil that emits more CO2 as it warms up, methane hydrates, carbon in the upper ocean, which comes out of solution as the ocean warms, and especially decreases in biomass as forest fires ramp up exponentially with increasing temperatures. So these factors put together give these temperature trajectories. There's, of course, uncertainty, but it's not uncertainty that I've quantified. You have these 6 scenarios, and from top to bottom, the warmest is the 2035 peak, and the doubled CO2 is the coolest. The Paris target in blue. In brown at 5 degrees is the highest temperature considered by the Stern Review. And it's generally, I call it when Kansas gets its hot as Las Vegas, and that's when civilization is collapsing with dramatic reduction in the population to a modest fraction of what it is now. This includes all the big albedo effects, sulfates, sea ice, snow, cloud cover, land ice, also includes more water vapor in the air. Notice that by 2100, many models just look out to then. Unless you're taking a lot of CO2 out of the air, you're looking at about 3.5 to about 4.5 degrees Celsius above 1750 by 2100, but the differences become greater after that. Few models go out that far, so worth observing. These are the 6 scenarios from left to right, with the warmest scenario shown by the bottom at 8.15 at the left, and the coolest one, the doubled CO2 removal at the right. The factors we've talked about go from top to bottom. The top line has the greatest average across the 6 cases. The second top has the second greatest average, and so forth down to the bottom one, which has the lowest average of the 6 cases. Notice the importance of the water vapor feedback and snow cover. Human emissions across these scenarios is third, then cloud cover changes from the albedo changes, sulfur, sea ice north and south, permafrost, warming the deep ocean. Notice that it's more when we emit more, which gives us longer to get to equilibrium. And then the other natural reservoirs of carbon. The effects of shrinking land ice are small and become appreciable in East Antarctica only in the high emission cases. So translating this to climate sensitivity, which is how much Earth warms when you double the CO2 level, and normally it's calculated as doubling CO2 level from immediately pre-industrial 280, which would be up to 560. Earlier on, by looking at the Vostok ice core, we got an estimate of 8 degrees. Actually, Earth's surface globally warmed 5 degrees over the period that it rose by 56%. If you extend that, it becomes 8 degrees Celsius for a doubling. But 2/3 the ice and snow vanished. That means it's not going to warm as much. And in particular, we'll use the figures at the left, cold turkey and phase out fossil fuels by 2050, magenta and orange. The average CO2 level is about 560 at 2400, and the average temperature is about 6 degrees Celsius, 2400. So that gets us an estimated climate sensitivity of 6 degrees Celsius. You can increase CO2 even more, and you get a different estimate, which will be still lower. And you see that from the 2035 peak, it's almost double 560, 9.3 degrees Celsius and rising, which suggests climate sensitivity over that next range is almost 4 degrees, which is less than 6 over the range we worry most about, and is up as high as 8 in the very heavily glaciated times of the Vostok ice cores. So what we need to do, stop putting carbon in the air and take it out big time. We may need to do solar radiation management as a supplement as well, but not as a substitute. Almost all the economists or anybody in the world agree we need to tax carbon across fossil fuels worldwide in proportion to carbon content, impose a tax upstream, start low, rise substantially and briskly on a preset trajectory, end subsidies for fossil fuels. I add that carbon tax credits for carbon removal from ambient air would be at the same rate that carbon emissions are taxed. There's one of my proposals for a price trajectory. The proceeds should be returned as equal dividends or tax credits to individuals. This helps poor people who generally don't use much carbon and penalizes rich people who do a lot, creates jobs and grows the GDP, grows the economy. The major methods to take carbon out of the air include direct air capture. You take the air capture, CO2 captured, pipe it deep underground into carbonate poor rocks like basalt, olivine, and it turns to carbonate rock within 2 years. Organic farms are the cheapest way now. They do a good bit, although they may just move soil or carbon from the lower levels to the upper levels of soil. We can accelerate rock weathering, which takes 1 gigaton per year, about 2 to 3% of what we emit out of the air anyway. Spreading it dust across the tropics or as small olivine gravel. Farm the oceans, bury biochar, stay there sometimes for millions of years. Holistic management, short rotation cattle grazing, but you need to watch out for methane emissions from cows, so you feed them red seaweed. Trees are wonderful things, but soils, as they warm up, will have less water. As a result, forest fires grow exponentially with temperature, and there's not a very good long-run solution, unfortunately. In summary, we must go carbon negative big time by 2050. If you have questions, you can contact me. You can go to my website, which has thousands of articles other people have written and a few that I've done, as well as several of my slideshows. So, thank you very much, and goodbye.